Hello community! Today we talk about some brand new 3D LLMs. You know, this is called Spatial AI, and we're gonna have a look at these brand new LLMs. And you might say, but who cares about Spatial AI when we have an OpenAI Developer Day and our 4 little bread crumblings are presented to us as developer? Should we not focus on OpenAI investor relations? No, we will focus on technology because there's another little tiny company called NVIDIA that just yesterday told in its investors, you know what is the new frontier for AI? Spatial AI. So this is where they will focus here their research efforts on. And if you're interested here, just a little reminder from yesterday where the real frontier of AI is. So let's start. What is spatial intelligence? Now, there's a simple definition that the ability of an AI agent to understand the 3D world that the agent is in and to reason within this 3D space configuration so that we know how to perform tasks in our 3D environment. This is what they call spatial intelligence. And we have a new framework, a new AI framework that is called Robin3D, and we will have a detailed look at this in my video. Now, Robin3D primarily focusing on developing the intelligence aspect of spatial AI. So to be absolutely precise, we are looking here at the learning capabilities, at the augmentation capabilities, how we can improve the performance, and not so much the general aspects of spatial AI. And to start off with, look, just 2 weeks ago, my goodness, so months ago here in AI real time, we have here on-demand spatial temporal understanding at arbitrary resolution, which is great to understand images, videos, and this is important, multi-view 3-dimensional scenes. Now, we are not focusing here about a new OpenAI speech, whatever functionality. We go the next step. Multi-view 3D scenes, because we are moving in a 3-dimensional space. And as I showed you weeks ago, we had here this vision transformer model, which is really nice with a compressor. And I could explain you here the inner work, or I could show you how the vision transformer operates here with the dynamic compressor in conjunction here with the large language model. But no, we want to go here an even further step. But to take this step, we have to understand the terms. We have to have clear definitions of what we are talking about. And there is a problem that I have, because there are terms like embodied AI that I do not understand precisely what is meant. So I looked it up, and you see here, January 5th, 2022, so in the Stone Age of AI, we had, as the authors write, an emerging paradigm shift from the area of the internet AI, I don't know what this is, to an embodied AI in 2022, where the AI algorithms and agents no longer learn data sets created from the internet. Now they learn from interactions with their environment from an egocentric perception similar to the humans. So in my understanding, hey, but this is exactly what AI agents are doing. No? I mean, the primary definition of the AI agent is that they interact in their 3D environment, that they can perform tasks, that they have a memory, that they have a function calling, a tool use capability, an augmentation capability, a planning capability based on the augmentation capability. So I understand here from the Stone Age that this embodied AI is here. But it goes here to the other side of the spectrum, where you see at the end of 2023, Google DeepMind had here this generalist agent for robotic manipulation. And they talk here about a multi-embodiment, multitask agent for robotic manipulation. So honestly, there's not a precise semantic definition. Well, of course, we go here to our little strawberry and I ask here for the precise definition of embodied AI after I fed some information to it. And then I said, and what is the definition of the robotic agent? And this is here for you. And I ask you for the key differences here for embodied AI and robotic agent. But honestly, I would use both terms more or less on the same footing. But let's talk about spatial intelligence. And let's focus here. Just 2 days ago, there was a brand new publication, Robin3D, improving here our 3D LLMs via robust instruction tuning. And this is a beautiful paper. Why? Because we talk about 3D LLMs, this means our LLMs can now understand our environment, the real-time environment we are in. And we simply do this with a 3D point cloud. And we do here the object identification, the segmentation before, and then we can argue about our environment. And maybe we can ask a robot to perform tasks, and the robot really understands here the complete positional embedding, and we can interact via a 3D LLM. Also, in my last video, I showed you here robotic AI agents with embodied semantic mapping in its non-parametric memory. This, if you want here, and you had a lot of questions, how is it possible that our little AI drone flying here in a disaster area can really establish here a three-dimensional environment here, this 3D point cloud? And today, if you want, we have now a deep dive on the technological implementation, the latest research on this technology, how to build it, that we can generate here our 3D LLM models of the real environmental data. Great. So here it is. This is the explanation of spatial intelligence in Robin3D. And I said, okay, this looks not so complicated. So what we have? Well, of course, we start here with a system prompt, beautiful. Then we have an instruction prompt, beautiful. And then we have some object ID defined by the system. We have our tokenizer, our embedding layer. And yet we can start now. We have now our training. No, wait a minute, because we have now the complete additional visual information. Either we have multi-view images, then the thing is rather easy. No? We have here Dino vision transformers. I have a video on this, where we have a two-dimensional projector, and the projector gives us here the two-dimensional features of two-dimensional multi-view images. But we go a step further. We go in a 3D environment, as you can see here. This is a study room from, let's say, a student at the Technology University in Munich. And we have a point cloud. We have a sofa, we have 3 desks. We have somewhere some chairs, beautiful, a pillow here on the sofa. You get it, the idea. So what do we use? We use now 2 simple software packages, Uni3D and Mask3D. Yes, you get it for the masking. What we get is our object features and the position embedding. And now we fuse here the features, but also with the position, X, Y, Z position of this. And we bring it together. And this is a new component, a new technology. I'm going to explain in a minute. The relation augmented projector. What it does, the output is 3-dimensional features. So what Dino and its 2D projector was doing, 2-dimensional features, now we have the same thing if you want here, 3-dimensional features here with the complete position embedding. Where is the sofa? Left, right, here, what is on the table, what is under the table, what is beneath the desk, where you know all those relations of objects that are now identified given the position. And then we can use our LLM to provide tasks, say what a robot should do, because now finally our LLM is able to understand the 3D environment that we are in and that the AI is in. And then finally we can go up and say, now we have the 3D data for our classical LLM training. And now you might say, hey, wait a minute, there's an unspecific layer. And they say there are 2 features here. And what they call this is the ID feature bonding layer. This is new. I'm going to explain this in a minute. And we have here, just as a preview, we have here that we position here specific object token to specific location. I'm going to explain why. And we have a post-vision ordering here of our tokens. That is quite funny to understand the reason why. So this is the whole thing, and then we train here our LLM, and you say, this looks simple, great. For my green grasshoppers here, more than a year ago, Uni3D, exploring unified 3D representation at scale. Real interesting code and models are available for you if you have never experienced Uni3D. And of course, Mask3D, the other object I told you, pre-training 2D vision transformers by learning Mask3D priors. And it is easy. You just take here an image here of this beautiful dorm room here at the University of Munich. And you see, my goodness, this really looks like my room. And then you have a pre-trained vision transformer backbone. And I showed you here instant segmentation, semantic segmentation, where are objects positioned, how can we identify here the objects. And This is it what you end up with. And I showed you also, I think 2 years ago or 1.5 years ago here, my videos here on visualizing the self-attention head in the last layer of a Dino vision transformer to understand here what Dino brings out here of the image. And if you want here, I've given you also the Python code here for a panoptic image segmentation with vision transformer and mask-to former. So you see each and every object is absolutely identified with a probability of correctness. But let's start now with Robin3D, and they have some beautiful new innovation. And the first one is a new data engine, a data generation engine. And you might say, what? Why we need new data? Well, the old data are not good enough. So therefore, we produce now 2 different types of additional instruction following training data. And on the one hand, we have the adversarial data, these are new, and the diverse data. This is also new by our RIG engine. And you might say, why? What are the current problems that we have? We have 2 problems with our current 3D LLM models. We have a lack of discriminative power and a limited generalization only. So, why does this happen? It's easy, because most existing 3D LLMs are trained with predominantly positive data. This means correct pairs of instruction and outputs. This makes the whole system prone to overfitting and beautiful hallucinating positive responses. Why? Because we only have positive responses. Imagine if we humans, we learn from our failures. If you have no failures in your dataset, if you only have success, the system only learns, hey, everything comes in is a success. So guess what? It hallucinates like crazy if it can't find not the success. So therefore, we have new adversarial data generated now by our RIG module, and it simply includes positive and negative examples, helping the model to learn to distinguish correct from incorrect responses. And this enhances here its discriminative ability quite a lot. In the other one, why have we limited generalization? Easy. We only have a similar data pattern structure. So existing datasets often follow a rigid instruction style, always the same boring style. And this limits a model flexibility, because if you question something that is not absolutely in this rigid instruction style, guess what? The model has problems understanding you. So simple solution, just train here with diverse data generated by our new RIG model that includes here different varied instruction style, boosting here the model's generalization. It can be so easy, and then the RIG model has generated instruction following data. They were used to train here 1 million samples. Beautiful. But you already have seen we have 2 new components here in our 3D point cloud that we have to do this. And the 2 new technology components, if you want, in the architecture are a projector and the bonding. Now, the projector first. No, it is not RAG, it is RAP. So the relation augmented projector. What it does, simple, it enhances here the spatial understanding by adding here a scene level context and the complete position information of all available, all detected 3D object features. This is it, and we're gonna have a look in detail in a minute. The ID feature bonding is real simple, and just this model strengthens here simply the link between the object IDs, and I will show you those, and the features. That's all. And this helps the model to refer to and ground the object correctly in response to the instruction. So here we go with our 3D point cloud. Here we have this beautiful basement. I don't know, I wouldn't call it an office here, study room here of 2-3 students here at the University of Munich. Beautiful. This is our point cloud. This is our real 3D environment. We have a sofa, we have 1, 2, 3 chairs, we have 1, 2, 3 desks, we have 2 bookshelves, a sofa and a pillow, and that's it. So now we bring in Robin3D. So what do we do? Different tasks that we want that the system is able to do. Scene level, category base. Can you find any bookshelf? Can you find a telephone in the image? Can you find the couch? Robin comes back and says, yes, object 1 and 2, bookshelf, 1, yeah, there's a bookshelf, 2, yeah, that's a huge bookshelf, great. Telephone? No fixed line telephone available, maybe this was it in the past. Couch, yeah, absolutely. We have a beautiful orange couch here and a little pillow, number 4, on the couch. Great. Then we go here, scene level, expression base. And we say, hey, please share the ID of the object that fits the following description, the pillow under the couch. And Robin understands that there is a semantic mistake and has said, hey, it is lying on the couch and it is object 4. So object 4 is our couch. Now, object 3 is our couch and object 4 is the pillow on the couch, but it is lying on and not under the couch. Corrected it. Beautiful. Other example, if you can, please share the ID of the object that fits the description, the mouse on the desk. And Robin comes back and says, yeah, here we are. This is the position XYZ coordinate of an object that is on the desk, and I identify this as a mouse. So you see, we have suddenly here a 3D positional understanding of all the objects and their relation to each other in the room. And this enables now 3-dimensional reasoning and instructions. And this is here the beauty of Robin. Another example, object level category base. And you can ask here, hybrid referring object classification, is it correct that the object 6 is a whiteboard, 7 is a table, and 8 is a clock? 6 could be a whiteboard, okay. 7 is a table, 7 is a chair. 8 is a clock, 8, yeah, this could be here. Optical distorted a little bit. A clock on the wall. Beautiful. Next one. Scene level expression base. You ask, hey, what is the small in blue and sits underneath the desk near the tall bookshelves in the room? And now, careful, this is tricky. Can you answer the question using a word or a phrase and provide all the IDs for object related to the question and answer? So it is not just give me the answer, but tell me that you understand the complete environment where our answer is positioned. So the answer now by Robin3D is, what is small and blue and sits under the desk near the tall bookshelves? So we have either this one or this one because we have 2 bookshelves. Now here we have something beautiful. We have here with number 10 in blue a trash can under number 9. But both objects now are identified here. The ID for object related, these are the bookshelves, and we have bookshelf number 1 and bookshelf number 2. So we have here 1 and 2. And the solution, of course, here is the trash can 10, the blue one. So you see, it knows here the relative positioning in the room, which is really nice. What is on top of the bed? Yeah, Robin says, hey, no idea because I cannot detect the bed. I just can detect here the sofa. You get the idea. So, summing up, our projector is a beautiful new model and enhances here the spatial understanding of adding a scene level context and all the position information of all the detected 3D object features in my environment. How we do this on a technological level? Well, 3 easy steps. As I already told you, what a coincidence. We have here Mask3D. So we tag the object features from Mask3D. These features represent the individual object in the scene, extracted using here a pre-trained 3D segmenter called Mask3D. We have the position embeddings. You know this, embeddings derive from the 3D coordinates of the object in the scene. And then we have some unified object features. Features come from a pre-trained 3D model called Uni3D, which produces object-centric features based on the 3D point cloud of each object. I've just given you an example. After this, they found out, hey, it's a good idea if we would normalize here the complete stuff. So what they did is said, okay, RAP applies now an L2 normalization to both the unified object features and the mask object features. And this normalization ensures that the features are on a comparable scale. Great. After the normalization here, this projector concatenates the unified object features and the mask object features along the channel dimensions. But wait, we have not learned yet. We just have constructed everything. So what is the easiest way? Hey, come on, we have a multi-layer perceptron transformation. Isn't that easy? And we have, of course, 2 separate MLPs. One MLP processes here the concatenated object features, what a surprise, and the other MLP processes the position embeddings, another great surprise. Okay, and then the output of both MLPs are then summed together not gonna believe it, to produce the final relation-aware 3D features, which now contain both the object level information and the spatial relationship data. We achieved our goal. We have it now. Isn't this simple and beautiful here in the implementation? So for my green grasshoppers, we understand the projector, enhance the spatial understanding by adding scene level context and position information for all the detected 3D object features. Great. Now a short summary. But we have a second problem. Remember, we had this strange ID feature bonding layer here in my explanation. So why do we have this? As it turns out here in this current model, multi-modal instruction following scenarios, it is crucial to refer to specific objects and accurately ground them within the 3D scenes. In the earlier methods, the current methodology that we use is append object ID to object features in an interleaved manner. But interestingly, this is not providing a strong enough connection between the object ID and the corresponding features. Now, the idea was simple. What can we do against this? Now, you're not gonna believe it. They had a very simple solution and they say, hey, you know what? Each object feature is now wrapped with two identical object ID tokens. So simply, we take an object ID token before, and we take the other the identical object ID token after the object feature. Reading this, I said, come on, you're gonna be joking. We're in October 24 and we have to do this trick to have a stronger bonding of the ID and the feature representation? Yes, that's simply it. And they say, hey, the first ID tokens, it connects to the object ID to its corresponding features, while the second ID token strengthens the link in the opposite direction. So we have a direction-depending positioning in our string, which is, wow. Okay, sorry. While the second ID token strengthens the link in the opposite direction, this means from the object features back to its ID. And this bidirectional connection really helps reinforce the association between the object ID and the features. Amazing, but you learn that the system is not able to do this, which is an indication that maybe this is not the final solution, this is not the most elegant solution, because, come on, we have to wrap here this up with between two identical sandwich object ID tokens. Okay, if it helps to improve the performance, yeah, but this is not the final. And then the second step is, of course, as I already showed you, the post-vision order. And now another time, a simple idea. The ordering of the token is so important that the model can improve its performance. You say, come on, this is not true. But yeah, we have just seen that the bidirectional orientation of the tokens is important. And now, where we place the vision tokens in relation to the complete input sequence is also of importance. It's crazy, I know, but it is. Sorry. So the IFB places now the vision token, this means the object ID and the feature pairs at the end of the input scene, right before the answer token, this means the output. And the reason for this, tell us the order, is to minimize really the distance in tokens between the vision information, our object ID and the features, and the final answer that the model generates. And it is really here, the closer the proximity, the more it helps the model to focus on the visual grounding information during the final stages of the three-dimensional reasoning process of our LLM. Amazing that we have to take care here about the proximity of tokens, but okay, if they tell us here, hey, this helps improve the performance, yeah, but also for me an indication. I don't think this is the final solution. I think it feels like, we are trying to implement something that we have not found yet the most elegant solution for this. So for my green grasshoppers, beautiful. Now we understand ID feature bonding mechanism. It simply enhances the model ability to ground the object in response to complex instruction, improving here its overall performance on the task that involves spatial reasoning, object referencing, and a complete 3D understanding of our environment. Great. Benchmark data. A lot of competitive 3D LLM models. If you know all of them, congratulations. I do not do this, but I can read that in the last line the authors tell us, look, our model here, our Robin3D, in green is simply performing the best, more or less, in all the different categories of the benchmark data that we have. And I have no other possibility to just trust their data. Okay, so where are we now here if you compare the current technology level to this new Robin3D idea? And it really shows us here, in contrast to the current 3D LLMs, that suffer non-performant at the two issues I told you, the discriminative weakness and the poor generalization capabilities of the model. This new Robin3D approach integrates here, as I told you at the beginning of the video, the new data, the adversarial and the diverse data set, along with two novel modules, RAP and IFB, that better process here the complex 3D spatial data and takes care about the bonding features and about the relative positioning. The result is that this Robin3D model significantly outperforms state-of-the-art methods, gives us here almost 8% improvement in the 3D grounding task and a 7% improvement in the 3D captioning task. And now the beauty is without needing task-specific fine-tuning, because this would really be hard to achieve on the fly. Great, beautiful. So now you understand here the inner working here of this brand new idea, Robin3D. This is now the methodology to understand here the complete, how to say this, positional information, our 3D point cloud information from a drone or maybe just from your iPhone or however you detect your environment, that now the next generation of LLM are able to understand the complete visual data in 3D grounding, in object identification. The LLM now understands here the positional reference, the relation of each and every object in relation to each other. And now it is so easy to define tasks to be performed, because now it is not just a virtual language models on your phone or on your computer, but now we have the ability to integrate here the AI in our real environment. So AI understands where we are living, how we are living, what are all the objects in our environment, how we can interact with those objects, and what possibilities are there for us in the future. I hope you found it interesting. I hope you had a little bit of fun here within this video. Maybe you learned something new, some new knowledge, and it would simply be great to see you in my next video.